Yeah, thank you very much. Thank you for sticking with me. So let's try to go from where we stopped last time. So last time, I defined the partition function of graph homomorphism or general multi-spin system. So we have a graph. And then to each edge, so it's undirected graph, we attach a k by k complex symmetric matrix A u v, A u v I j, and the graph homomorphism partition function or multi-spin system partition function goes as follows. So you take the sum over all possible colorings of the vertices in k colors. And then what you do, you take the product over all edges, the corresponding element of the matrix, right? And then I said that we can prove zero freeness. So there was a theorem with Pablo Soberon, which says that for if the entries of these matrices are sort of within an absolute constant divided by the largest degree of the vertex, so, and the constant we can actually choose, for example, this one. So then the graph homomorphism function is not zero. We can do that. So then, which gives us the sort of the disk-shaped zero-free set around 1. Right, so 1. And if we, of the radius gamma over delta, if we pick those aij's from this disk, then it's non-zero. Then there is another theorem that sort of gives you the strip condition, so which I think from sort of combinatorial optimization, computational purpose is a bit more interesting. So basically it says that if you pick, so let delta indexed by delta, just to avoid the confusion, so be the tangent of, let's see, yeah, so tangent of pi over 4 delta minus 1 for for delta at least 4, and tangent of pi over 9 for delta at least 3. So then for any right, yeah, no, for delta equal 3. So the case delta equal 2 really, so you have a bunch of cycles. Let's not think about it, so it's not interesting. So delta equal 3, yeah, thank you. So then for any delta less than this one, there is epsilon positive such that if the real parts are close to 1 within this distance delta, and the imaginary parts are pinched, then this thing is not 0. And that gives us a strip that sort of in kind of general position with this circle, right? So it covers part of it, but it sticks out and covers more on the real line that we might be interested in. So, and as I said, so by interpolation, so in all these situations, this function therefore is approximable. So the standard, the standard interpolation lemma that I proved last time, so it gives you a quasi-polynomial time algorithm, but if you involve some sorcery of Patel and regs, so in polynomial time, as long as the largest degree is fixed in advance. So that that technique, that trick, is actually quite a nice trick, is that you can compute sort of those Taylor coefficients kind of faster than just by direct enumeration. And I think that's where we stopped more or less last time, right?
And how does epsilon depend on delta?
It's not so bad. It's something like the difference squared, right? So just like in the case of the permanent. And as I said so last time, I repeat it now. So the proofs are basically somewhat embellished versions for the proof for the permanent. So for the permanent, we used some relations between subpermanents. And here, what we do, we sort of pin some of the values of this function. We say that, okay, so what used to be subpermanent will be the same function but restricted onto the colorings that give to some vertices prescribed colors. And then we look at the angles. And then we do this middle school thing, right, that I talked about yesterday. So
why do you get different parameters here than in the permanent case? Because the angle phi over 2 is replaced with something.
Exactly right, yes.
So you have a smaller angle.
The smaller angle, yes.
Is it with phi?
Well, it has to depend on the degree. You know, it depends on the degree.
Is that exactly that angle with phi over?
That I forgot. Maybe it is, maybe it isn't. I forgot. Sorry. Maybe it is. But so the proof basically leads you to the angle that you choose, right?
And then you prove a lemma which is similar to the one you showed yesterday.
I think I proved the same lemma. Or yeah, there is some.
With a different angle, right?
No, so what? Well, yes, yes. So it's all the same. So the bottom line is that sort of easy, right? So it's the same idea, right? What I'd like to do now, I'd like to zoom in some special choices. So some special choices. So in particular, one special choice is when all these matrices are the same. And they look as follows. So they have one off the diagonal and z on the diagonal. It's the same entry. And that's what corresponds to what combinatorialists call colorings, and physicists call Potts model. So in this case, this functional becomes really simple. So what you do, you still take the sum over all colorings, so k colors, or you say, if you physics, you say spins, and then what you do, you take z to the number of sort of monochromatic edges, number of edges uv, right, such that the coloring on the endpoints coincide, all right? So that's it's pretty clear, right? So that if they don't, you pick up 1 in the product. If they do, you pick up that parameter z. And so this model is called ferromagnetic So if the absolute value of z is greater than 1, well, if honestly, if z is real, greater than 1, and anti-ferromagnetic if z is less than 1, or still positive, not negative, right? Because what happens, so why so? So ferromagnetic means that this partition function somehow likes contributions with of the vertices with identical spins. Likes the correlation of spins. And anti-ferromagnetic, so the contribution of identical spins on the edges is kind of getting small, all right? So it dislikes them. So in particular, so if z equals 0, so the extreme anti-ferromagnetic case, then this thing is just the number of proper k colorings. Something that we certainly would like to compute, right? So if we just discount any colorings that's illegal that colors 2 endpoints of an edge with the same color, right? So that's one good example. So there is some activity underway, very vigorous, I must say. So I can hardly keep track of it. Although I'm very interested in it, to actually to find the zero-free region for this in this particular case. So the latest thing that's available in the public domain is a preprint by Bench Davis, Patel, and Rex, 2018, which says that if k is the number of colors is large enough, if it's at least e times delta, delta again is the largest degree of the vertex, and e is this, right? Well, it goes on, as you're probably aware. Yeah. So then, this functional is not 0 in a neighborhood of the interval. That's what we care about, in the neighborhood of 0, 1 interval. So we have a zero free region here. So zero free. Zero free region. So which automatically, through the interpolation, allows us to count proper coloring. So approximation polynomial time deterministic polynomial time algorithm to count proper coloring, proper K colorings. The region does not. It may depend, though, on delta. So once you fix the max degree, you're fine. So then you can sort of reinterpolate it from 0 to 1. So we can interpolate from 1 to 0. That's the sort of reasonable thing to do here. Right. And so that's the best available in the public domain. Privately, better bounds unknown, but I'm not at the liberty to disclose that. So there is a correlation decay, right, which right, yes. But I just wanted to mention that. And there is a question that I think there is a, which is quite plausible, that it's has a positive answer. So question, so is it true that a similar result holds if K is greater than or equal to 1 plus epsilon times delta for arbitrarily small epsilon, or even if K is at least delta plus 1. So there is a so it's open. It would be nice to prove. So by the way, so the proof that they got is the really embellished version again of, well, they say, Rex told me that he was inspired by the proof for the permanent. So it's again some manipulation with sort of recurrence relations. Yeah. So it's still, it's still inferior to what you can get by correlation decay, and also inferior to what you can get from Markov chains, randomized Monte Carlo, which gives you 11 over 6 minus epsilon delta. Right, so epsilon is small but positive. Right. So that's open, and I certainly would have liked to close it, and that's, yeah.
So the same way for the permanent, you talked about like a lower bound against the style of proof technique.
Yes.
So for these types of things, are there lower bounds against the style of proof technique?
That's
Above, like, C times delta for some.
that I don't know.
Because I was sort of curious that, like, for the Markov chain thing, there are natural barriers at 2. There are natural barriers at 11. There are at least. Like,
Yes. So
to be.
there seems to be some parallelism here going on, but it's still at a very early stage, right? So that's the best known, but Yeah, I hope very much that it will be resolved in lifetimes in a positive way, right? One off the diagonal, right? So that you penalize coloring with the same color, right? Yeah. Okay. So other.
For deterministic algorithms, this is the best.
No, that's not the best. This is not the best. Yeah. So correlation decay gives, as David mentioned, a better thing. Yeah. So in the second digit. Right. Right. So far we kind of argued that complex analysis helps you to compute something. I'd like to present one example where complex analysis predicts that they're not complex analysis. The complexity predicts some fact from complex analysis that there must be zeros somewhere. Yeah. So that corresponds to the case. So that was this particular choice. So it's a coloring spot model. So now let's choose, again, all the matrices the same, and choose them like they depending on epsilon, like epsilon on the diagonal, 1 off the diagonal. Epsilon is positive, but say small, right? So we can do that. Then I have to introduce a definition. So if the set S is set of vertices, then the cut associated with the set is just the number of edges with one vertex in the set and the other not in the set. So that's the cut of the associated with the set S. And the max cut is just the maximum of all of all cuts, right, over all S. So cut is a number here. It's just the number of edges that you destroy by picking one element S and the other is not. And the max cut is the largest among all. So then you can quickly figure out that what's going on, that this functional computes something going on with cuts. So what do we have here? So we count every coloring, every function that sends vertices to different numbers, to different colors with coefficient 1, and gives you epsilon if they're colored the same way. So it's in the, so I guess it's a particular case of the Potts model. So it's the sum overall maps from, we color in 2 colors, and we get epsilon to the number of, just like there, the edges where the colorings are the same. But then, because there are only 2 colors, we can express it in terms of cuts. So we can write it as epsilon to the negative number of edges, sum of where all subsets in the number of vertices, epsilon to the negative cut, right, associated with this subset. Well, I didn't use the, right. So we have this. And then we begin to realize that something interesting happens. So as
So why do you get negative? It's supposed to be polynomial epsilon, right?
it's supposed to be, so maybe it's plus here. Okay, that's better. Right. Yeah, thank you. Yeah, so then, why did I put minus? I don't know. Yeah, but thank you. So, right, so it should be plus. So then we realize that something happens. So as epsilon goes to 0, so by the way, so this is also, so it's a Potts model, but since k equal 2, it's only 2 colors, that's also anti-ferromagnetic magnetic Ising model. Right, so then what happens here is as epsilon goes to 0, so if we look at, I understand why I put negative, so because I'll bring it on the other side just in a second. So then the main contribution to epsilon to the negative e times the partition function comes from epsilon to the negative max cut, right? So the epsilon to the negative max cut. So we can actually, so if we could compute it, then we could have approximated if the value of the max cut, something what Michel did, right? So last millennium, right? Right. So and then there are hardness results. So even as delta equal 3, so even for graphs with the largest degree, the vertex equal 3, so it is sharply hard to approximate max cut within certain constant factor. So maybe pretty big, but there is some absolute constant. So we know that approximating within that constant is really hard. So that's why we got Karpinski, right? So, and
By the way, probably not sharp P.
not NP?
NP.
NP. Oh, right. Yeah, right. Yeah, thank you. Right, NP hard, right. So that Bergman and Karpinski, right? So what does it tell you? It tells you that in this particular situation, you cannot, or you should not expect to have zero-free region up to the 0. So there is a natural barrier somewhere. It's probably what you get from that. It's Berman, sorry. Yeah. What you get from that is that there is some wall here. After which you got to have zeros close to the real axis, as close as you can possibly get.
So why can't this wall go through 0?
Well, because then P, well, true, it can, but then P is equal to NP. And the benefits of that certainly overweigh making a wrong prediction here. Yeah, so I'll gladly be wrong.
No,
Yeah.
just straight through 0, not to the left, but straight through 0.
Straight through 0, no, because to approximate within like constant, I don't know, million. That means that it suffices to get kind of really close, but not to 0, right? And we cannot. Yeah, we cannot. Right. So that's sort of a prediction of the 0 behavior in ferromagnetic Ising model based on sort of our complexity beliefs. That if we believe that P is not equal to NP, and we really have no choice, right? But to believe that we cannot prove anything, we cannot disprove anything. So it's just a matter of belief. So then there ought to be zeros, right? So we cannot pull that zero-free region all the way. So, and notice that that case is different from the permanent, where we could sort of come arbitrarily close. Right. So, okay, right.
Do we have any understanding of what those zeros look like without condition?
Well, I personally don't, but maybe there are people who know, right? Maybe physicists know better. Yeah, but I personally, I don't know. Anti-ferromagnetic Ising, as I understand, are pretty complicated, right? So that's, yeah. Well, I thought it's a nice illustration that sort of goes the other way, that it predicts that there ought to be, right? That was really close. Right. Maybe this way you can, I don't know, prove or disprove the Riemann hypothesis. So if P is not in P, then the roots either have to be there or have to be not there. Yeah. So just related to something that you cannot do either, but at least you involve more people into the discussion, right? Yeah. Okay.
So I didn't understand. So what is the difference between the sports model story and that story?
Oh,
Where you have the approximation in that?
yeah. So here what happens is the approximation, because I use many colors, and that many colors create zero-free region. But as I tighten the number of colors just to 2, then things become kind of hard. Yeah. So other concerns or objections? So that's last half. As I promised in the title, I'll try to relate it to physics, to the physics of phase transition, and then present my wildest pipe dreams about how the things may develop. So if, again, there are no objections. They're not extremely wild. They're kind of just some wish list, right? Yeah.
So maybe it was a joke about looking at a function, but question related to that. This lemma from yesterday about having very few coefficients, needing very few coefficients, was for polynomials of degree n. Do you have some extension to some classes, maybe of
Rational functions certainly work the same. Yeah.
entire function?
Entire function, you have to bound the growth, right? So
Yeah, boundary growth, but with many zeros.
as many zeros, right?
Infinitely many.
No, the honest answer is I don't. I'd like to have that. Just would be a nice thing to have handy if it's needed. Like it's,
There are other models for which are exhibit similar arguments, like
Yeah.
or for which you know that there are zeros.
right.
Can't one build a gadget from one to the other and create essentially a cut version of
Cut the version. That I don't know. I don't know. Yeah, I don't know. But okay, so then I'd like to sort of go to the final stretch, so connect it to physics, and then sort of disconnect it from physics to say that physics marches its own way, and we are left here struggling with complexity, and then sort of present a wish list, what we would like to do. So the whole activity, of course, was started by Lee and Young. So in Lee and Young in 1952, they published 2 groundbreaking papers on the phase transition and zeros. So what's the idea? So let's look at this particular example. So they of course did it for the Ising model, ferromagnetic. So I'll do for the Potts model. So look at the Potts model. So then we call assignment of colors, as physicists do, we call it configuration. And then we say that the probability of, so we make the set of all configurations, which is a finite set. We make the probability space. So the probability of the configuration is z, well, to the number of miscolored edges. Divided by, so that it's sum of probabilities is 1. So divided by, of course, the partition function. So the probabilities sum up to 1. So what is z here? Z is basically e to the, in antiferromagnetic case, -1 over T, where T is the temperature. Right. So. Yes. So then they say, okay, so let's look at this partition function. So, and certainly in terms of z or t, there cannot be positive real roots because you just summing up some positive numbers, you cannot get 0. But what they said that suppose there is a series, it's sort of a series, a sequence rather, of graphs growing in some regular way, so that the number of vertices grows. Such that the limit as n goes to infinity, so we take the log of the partition function and divided by the number of vertices. So the limit exists, and it's called the pressure, right? So exists, right? So that corresponds to basically to realistic physical system. There, the graph is so big that it's like infinite. It's like infinite lattice. So always think of some sort of regular growing graph. So it's basically lattice what they care about. And that's probably the reason, which can be very confusing, why physicists call graphs lattices. So if you're just into the business and trying to understand something, it says, consider a lattice. Hey, where's this lattice? There's no lattice, but it's a graph, right? So, and we make it bigger and bigger. So what they say, what may happen is that the complex zeros, so there is only one parameter, the complex zeros of the partition function converge to positive real point, which then deserves a special name called critical temperature. Which may, or may not, but which may signify a phase transition. So the picture is as follows. So you have a positive real axis, and then there is a bunch of complex zeros, but as the graphs grow, they just happen to converge to positive real number. Right. And why do they say that it may actually signify phase transition? Because what happens is that that pressure changes its differentiable properties. Asymptotically, it hits zero, so it may, doesn't have to, but it may become like non-differentiable or even discontinuous. Or there are examples I learned recently. The very fine phase transition, then this function actually stays C infinity, but ceases to be analytic, which is quite remarkable, I think. Yeah. So, and the phase transition in physical terms means that something big happens. So you have either like the water, the liquid becoming gas or becoming solid, or some magnetic properties acquired and lost, because, well, it's something related to discontinuity of this thing, right? So, and then there are, of course, examples of, so what I want to keep, yeah, I'll probably raise the max cut star. So there are examples of problems where this type of Lee-Young phase transition and critical temperatures are also bounds for computability. So there are problems. There are examples where the phase transition is also the critical temperature is a bound for approximability. And so one of the most famous examples is what's called the hardcore model. Or in combinatorial terms, it's called independence polynomial. And it corresponds to the graph homomorphism partition function. There the matrix is something like this. So then there is a bound, there is a critical temperature by the result of Dor weights. 2006. And Ellen Sly, who's here, and Sun, I don't know if he's here. Oh, yeah, right. So they both proved that this also great, also the bound for approximability, right? So, and there are, yeah, so that kind of makes us feel good about ourselves because we relate complexity to physics. So till the water boils, everything's fine. Once it gets boiling, forget about it, right? So till the ice melts, everything's fine. Once it starts melting, well, too bad. So it's
The other way around.
okay, yeah, but you got it. Yeah. So once it's condensation, of course, right? So once it has become liquid, right? But here I'm starting with sort of a pipe dream wish list. So why? So question. Why? Maybe in some cases, can't we jump over a critical temperature, the critical temperature? So meaning what? Meaning that, okay, so you have your real line. You want to interpolate from 0 to 1. Unfortunately, sort of evil zeros condense to the critical temperature here and prevent you from doing that. But the interpolation lemma allowed us to use all the complex plane at our disposal. Why can't we just, I'll write it in green, the color of hope. So why can't we do this? Right, so that would, so I don't know if there is any meaning in physics terms there. So that would correspond to like cooling regime going into complex temperatures. So physicists know many things. So are there complex temperatures in the world? So in principle, so that would allow us to do that, to go over and sort of to bypass the phase transition, right? So of course you can construct artificial examples that allow you to do exactly that. I don't know of a single natural example where this sort of complex bridge, actually the rainbow, right? Follow the rainbow. So exists. Right, so the natural example would have been like the matching polynomial, which we discussed last time. So which has, by Hellman-Lieb theorem, has all roots negative real, and so other like natural classes of graphs where we can, for example, compute its value at some negative real number by bypassing all the roots. So in general, so there is a paper by Goldberg, Leslie Bezakova, Yvonne Galanis, and Adena Stefankovich, right? There's Stefankovich that say that in general that's a sharp p-har problem, but are there any natural examples where such a bridge actually can be built, right? So that's one thing where sort of we can somehow bypass that physics of the phase transition. But again, I don't know of any natural examples. So, are there any objections to that? Yeah, I imagine, well, yes, because you exponentiate them, right? Yeah, but here they are kind of, well, maybe quantum thinks that's what they do, right? So another thing that I'd like to, again, to present a wish list. So can we just jump over singularities no matter what, over zeros? So can we jump over the reals no matter what? Over the roots. So can there be the following situation? So suppose that we have, again, so we want to interpolate between 0 and 1. So here is 0, here is 1, and we want to interpolate, but what happens is that there are fans of evil zeros right here, or maybe even right there. So whatever we try to squeeze is not going to get through because it's too thin, right? So can we introduce new variables say instead of a polynomial p of z, can we consider a polynomial of two variables, say z and w, such that at 0 we get p of z, and also at 1. And there is a sleeve to go from 0, 0 to 1, 1, but this time in C2, right? And in principle, I can convince you that it's always possible. It's not my argument. It's the argument of Mark Rudolphson, who just observed that you can think of polynomial two variables as a family of polynomials in one variable. And that turns out to be crucial. So here's what I do. Just follow my hands, right? I'm going to use this variable w to move the zeros up, move zeros down, down, and I cleared myself a way to interpolate from 0 to 1. I interpolate, and then I close them back. I move zeros back, right? So I interpolate it. So the trouble, of course, that's just a theory, you know. How do you do that? Practice. That's not clear at all, right? I don't know of any single example. Worse, actually, I don't know of a single example of a situation like this, actually, because what happens in the problems that we know are probably hard, zeros actually converge to 1. They're kind of dense around there. So we can start jumping, but we have nowhere to land, right? And that's certainly pretty bad. But if there was this sort of a launching pad and a landing pad, can we do so efficiently the thing, or maybe at random, right? And the final sort of wildest wildest remark here is that that I will not even put on board. So maybe what Markov chains do, something like this. Maybe you can interpret what Markov chains do because they seem to ignore complex singularities, that they introduce an awful lot of variables and then somehow find a random path in that huge space of a huge dimension that kind of avoids all possible singularities. Right. So that's, yeah, I have 2 minutes or? Yeah, okay. So that's perhaps the wildest kind of thing. Right. So maybe the last thing I'd like to say that even zeros somehow are not necessarily an obstacle to interpolation. So for example, the Lee-Young circle theorem um, 1952, which corresponds to the ferromagnetic Ising problem, says that if A is Hermitian and all the entries do not exceed 1 and the absolute value, then the roots of the polynomial, which is really a partition function, the ferromagnetic Ising problem with magnetic field. So you take the sum over all subsets, the set 1 to n, z to the cardinality of the subset product over all cuts over a cut associated with this subset. So the roots of this polynomial lie on the circle z equal 1 in the absolute value. Right? So they're all here. And it's known that, for example, if you pick a real non-negative matrix, then they're dense there, which means that they come as close to 1 as possible. Right? So, and then there is a Markov chain based algorithm by Jerome Sinclair. (1993), I believe, which does approximate computation at z equal 1 without even caring about any complex roots getting anywhere close. Right. So somehow, I mean, the bottom line is of these examples kind of well, maybe all these examples kind of sad. It says that maybe complexity is not reducible to anything at all. Maybe it will always fool us and have the last laugh. So whenever we think that we finally kind of caged it, so it's zeros, it's phase transition, it's whatnot, it will find a way around and say, no, it isn't. It's something else. So yeah, I guess, yeah, thank you very much. So that's it. Yeah, so they do get close to 1. So if you have a graph with bounded degree, then there was a recent result of Peters and Rex that says that if the bonds are close enough to 1, which means that they're not awfully strong, then there is a sector. Sector opens around 1, which is 0 free. But if without that condition, we don't even know. So I think they can be dense. Yeah, without that condition, right. So they can arbitrarily close come to 1, even in the bounded degree situation.
Yeah,
Right.
Can you get a lower bound for the number of those zeros?
For the number,
Using the same line of reasoning.
well, not right now. So I have to think. I don't know right now. No.
And another thing, so number of zeros can be written as a integral of logarithmic derivative.
Yeah.
Can you estimate this integral? Maybe to give another.
Jensen's formula are very helpful. That's exactly what Mehraban and Leora Dar and Said Mehraban did. Mehraban, he's a great student here, right? So, or at X. So they used it to prove that permanence of complex Gaussian matrices with entries variance 1, and the expectation goes to 0 very, very slowly, but still goes to 0, like 1 over log n. Then with probability 1, as n grows, you can approximate the permanence of this matrix. They used exactly this reasoning. They used Jensen's formula. And so the funny thing about it is that if they could make the expectation to go to 0 a little faster, like, I don't know, 1 over square root of n or something, 1 over n, then there is no boson-based quantum supremacy. So then we can kind of steamroll over some of the yet non-existent quantum computers. Yeah. Yeah, by the way, now I think I know. No, I still don't know the answer to your first question. I thought I knew, but I don't.